Hi, welcome to this lecture. This is Vikas from IARE Data Science Section C. The subject is chemistry. The topic we are going fluidic calorimetric sensor designed for hardness detection. So we are going to detect hardness using a fluid calorimetric sensor design for water hardness detection. Now let's go into the introduction to both domestic and industrial users. Like water hardness cause lots of decision problems, so water hardness is great concern to both the domestical and the ones which come to homes or the industrial users. It is caused by compounds of calcium and magnesium and variety of other materials. Hardness is caused by the components of calcium and magnesium and many other variety elements, but mostly of calcium and magnesium. As the concentration of calcium is found in Ca plus 2 in the aqueous state, and magnesium Mg plus 2 are usually greater than other alkaline earth ions. Like alkaline earth ions, hardness is equated to Ca plus 2 plus Mg plus 2. The amount of dissolved calcium and magnesium in water, like how much amount of how hard the water. Water hardness is typically classified. Like water hardness is classified into four different types. They are like soft, which is okay to use, moderately hard and very hard. Soft one per liter, which is 0. And moderately hard. It ranges from 0.61 to 1.2 millimole per liter. And the one which is hard is ranging from 1.21 to 1.80 millimole per liter. And the one which is very hard is greater than 1.18 1 millimole per liter. Hard water creates spots in glassware, built up on pots, rings around the bathtub and toilet bowl, and reduces efficiency of soap and detergents. Besides this, hard water also clogs pipes from households to industrial installations due to scale buildup, which can lead to breakdown and eventually costly repairs. In addition to all the above factors, too much of calcium and magnesium in drinking water can be determined to human bodies. Previous and current works in detecting water hardness includes flow batch photometric system, photometric sensor array, fluorescent molecular beacon wave sensors, and so on. The proposed sensor array system is used just in ion selective electrode, a reference electrode, and complex processing to determine calcium and total hardness of water. There are commercially available devices that can detect water hardness along with determining Ca plus 2 and Mg plus 2 concentration. Now let's move to the next slide. This is more extensive into the introduction. A calorimetric can be used to detect water hardness and also the concentration of calcium and magnesium ions in the sample. However, commercially available calorimetric meters are in ranges of hundred to thousands of dollars. This is more costly, like calorimeters, which are very costly, so a lot of people can't use that. There are also test kits available commercially that contains multiple items, including chemicals required to perform water hardness test, which can eventually become tedious and confusing. It's like confusing. On the other hand, single or multi LED and various types of detectors based on observance sensors are well investigated and summarized. Beside this, 3D printing is rapidly growing technology and is capable of printing structures. Our purposed designs uses LEDs and photodiodes and integrates them into one unit with the help of 3D printing and printed relatively at low price. Like the previous calorimeter is like cost of thousands of dollars, but the 3D printing like it costs less price. It will thus eliminate the use and handling of multiple items and most importantly chemicals. Our purpose sensor is not our purposed sensor is not intended to perform comprehensive water hardness detection but act as reductant unit in existing systems. For instances, we are targeting an example for a water softener. The sensor may be used in average households where consumers can install it with their existing water softener system, a protective application area. The sensor can then indicate whether the water is hard or soft just by checking the total hardness. Threshold value of soft water which is around 0.6 or 60 mg, which is of normal moderate lay which is 1.8, so on. Based on the information, the consumer can determine whether to replenish their water softener system or not. In the following sections, the next slides we'll discuss about the theory of complexometry and calorimetry detailedly, experimental procedure, and finally elaborate on the results. Like in the next slides, we'll be discussing about that. Let's see figure 3. Chemical structures of calamite. Figure 2 is EDTA, hexaprotic and tetraprotic. In tetraprotic, two nitrogens it contains two carbons. And figure 3 is of benzene rings. And moreover, let's observe these figures EDTA, the figure 2, and third one is of structure. Let's go to theory. Complexometric. It's complexometric is also known as complexometric titration. Is a titration based on complex formations. Complexometric is also known as complexometric titration, and titration is based on complex formations. Metal ions, like metal ions are Lewis acids, accepting electron pairs from electron donating ligands that are Lewis bases. Metal ions are Lewis acids, accepting electron pairs from electron donating ligands that are Lewis bases. When ligand binds to a metal ion through more than one ligand atom, it is known as multidentate or settling ligand. Like when a ligand binds to two or more ligand atoms, it is called multidentate ligand. Ethylene diamine tetraacid acid, which is also in short form is known as EDTA, is well known multidentate ligand or chelator. It is usually used as it is disodium dihydrate salt. It is an hexaprotic system designated by H6Y2 plus, where the highlighted acidic hydrogen atoms are lodged upon metal complex formation. Like in this slide, we have discussed about like water multidentate ligands, and an example of that is EDTA, which is a best example for multidentate ligand. Like multidentate ligands are like a ligand which is bind to two or more ligand atoms. Metal ions are Lewis acid. This is complexometric, is also known as complexometric titration. It is the titration is based on complex formations, complex molecules. Like see, calcium plus 2 reacts with Y minus 4, it gives CaY minus 2. The Kf of that value is like 5.01 into 10 power 10. It's very big and very big, and but it's less than Mgy2 minus. The Kf of Mgy2 minus is 4.9 into 10 power 8. However, the neutral acids is tetraprotic and represented as H4Y. The neutral acids are tetraprotic. It is represented as H4Y. EDTA forms strong complexes with nearly every metal ion carrying more than 1 unit positive charge. The stoichiometric for EDTA is 1:1, which means it binds to metals like Ca plus 2 and Mg plus 2 in the ratio 1:1. The stability of metal complex EDTA is dependent on the pH of the solution. The complexes of divalent metals are stable in ammonical solution. By varying pH of a solution, it can be decided which metals will be titrated with EDTA and which will not be. For Ca plus 2 and Mg plus 2, the complexation reaction with Y4 minus and corresponding formation constants Kf are given in the above equations. They are been given. Ca plus 2 and Mg plus 2 are mostly causing hardness. That's why we are mostly discussing about Ca plus 2 and Mg plus 2. Let's go to the let's go to like see Ca plus 2 plus Hy minus 3. The reaction is CaY2 minus plus H plus. The Kf of this is 1.8 into 10 power 10, and Mg plus 2 plus Hy3 minus gives rise to Mgy minus 2. H plus is like Kf is equals to 1.7 into 10 power 8. The formation constant, which higher values mean that the above reactions will go to complexation if EDTA exists in completely deprotonated, means which does not have any proton form. Moreover, the greater the stability of complex, the sharper the endpoints of the titration would be. Like if there is more stability of the complex, the sharper the endpoints of titration will be. To ensure that the titrate is in completely deprotonated form, pH value greater than 12 are necessary. Like to ensure titrate is in deprotonated form, pH values are kept more than 12. Like which they are like basis pH. However, however at pH 12, both calcium and magnesium precipitate in the solution. Therefore, titration is generally carried out at pH 10, at which portion of EDTA is in Hy3 minus form, and additional complexation reactions and conditional formation constants are given by. In the now let's see when Mg cluster is reacted with Hin-2 minus, which is in blue color, it gives Mgin minus, which is in wine red color, and a proton is there H plus. EDTA forms a weaker complex with Mg than Ca plus 2. Ca plus 2 reacts like when both Ca plus 2 and Mg plus 2 are given. EDTA reacts with Ca plus 2 first, because EDTA forms weaker complexes with Mg plus 2. Now let's see the reaction with Ca plus 2, which reacts with Mgin minus, which we got in the above reaction, which is in wine red color, plus Y4 minus, it gives Ca minus 2 plus Mgin. After all Ca plus 2 is titrated, EDTA reacts with Mgin. The one which we got in the above reaction, Mgin minus, wine red color plus Y4. It gives MgY2 minus plus In3 minus. In3 minus is colorless. Again In3 minus, colorless one, will react with water, which gives HIN minus to blue color plus OH minus. In the first reaction we got H plus, and the last we got OH minus. Now let's go to the next slide. Both EDTA and Ca plus 2. Both EDTA and Ca plus 2 and Mg plus 2 ions are colorless. These all are colorless. Therefore, a visual indication is needed to detect the endpoint in EDTA titration. There are like colorless, so we need an indication to detect titration of EDTA, right? So that's why we are going to give a technique. The most common technique is used to use a metal ion indicator. Metal ion indicators are compounds whose color changes when they bind to a metal ion. There are several metal ion indicators available, such as the calgamite, xylol, orange, and violet. Useful indicators must bind metal less strongly than EDTA does. Both calamite have been used to detect water hardness. However, calgamite provides a sharper endpoint and has longer shelf life than chrome black tea. 1-2 hydroxy 5-methyl 1-phenylazo 2-naphthalone 4-sulfonic acid or calgamite. Figure 3 was proposed as a general purpose. We saw in the first or third slide, like calgamite's structure was given. The IPAC formula of that was this 1 dash was proposed as a general purpose metal ochromic indicator through principally for calcium and magnesium by Lindstrom. When calgamite is added to water sample at pH 10, it will react with the Ca plus 2 and Mg plus 2, and color of the solution will turn into wine red. As EDTA is added, it will first react with any free Ca plus 2, Mg plus 2, then start to react with colored complex. Spectrophotometry is a procedure. It's like a procedure to use light to measure chemical concentration. Like spectrometry is a procedure which is used to uses light to measure chemical concentrations. Colorimetric analysis is adopted as it is uses visible radiations to detect and determine the concentration of colored compounds. Like spectrometry uses light, and calorimetry is using visible radiation. This is the difference between both. The intensity of light decreases as it passes through a solution. Like intensity of light as usually decreases when it passes through a solution. The amount of light passed through and absorbed by a solution is given by transmittance T and absorbance A respectively. T is equals to P by P naught, and A is equals to log of P naught by P is equals to minus log of T. Because T is P by P naught, which we write like that, log T minus log T will become. P naught is like initial intensity, P is like final intensity of light. Experimental setup and process. The prototype of the sensor was designed initially in SolidWorks and a product of Dassault System SolidWorks. Then it was printed using 3D printer dimension allied, which uses fused modeling technology to print prototypes. The material used to print the prototype was acrylonite butadiene styrene ABS, a common thermoplastic. Thermoplastic is like a polymer. This is a thermoplastic is a type of polymer. The overall dimension of the prototype was 30 mm into 40 into 15. 10 mm, 30 mm, 40 mm channel was embedded to hold the water sample. The prototype has two housings for two LEDs, one blue, one red, and the two housings for two photodiodes. The path length that light had to cover in the in this prototype was 10 mm. A square opening was created for the photodiode housing, and an iris was created for LED housing. LED housing. All the openings were all the openings were closed off with transparent plastic slides appropriately cut to the size of the openings. The epoxy was applied between the slides and a prototype body to prevent any leakage of the sample. A circular inlet and outlet were created to inject sample in and out of the channel. The path length that light had to cover in this prototype was just 10 mm. This is the diagram of that. As soon as the solution was mixed with the water sample, it turned red. The top of the channel was covered with blank colored slide and voltage readings was recorded. This is the diagrams of voltage and records. The results. Preliminary results on the work has been presented. Figure 7 and 8 were this both will be like explaining how the results have been given, and the conclusion. We have then EDTA is added to the solution. It turns blue, prompting voltage drop across the photodiode. We have presented a sensor that detects hardness in water sample based on concepts of compleximetric titration, calorimetric analysis. Thank you everyone.